we shall continue our study on the hardware security class. So, we shall be continuing our pursuit to find out an efficient and compact AES S-box. In particular, in the last class we were talking about polynomial basis representation. So, we shall be continuing to look into the normal basis domain, trying to see that whether in the normal basis domain we have more opportunities of optimization. So, in today's class what I will try to cover up is essentially try to work out the circuit optimizations that we were trying to see in context of polynomial basis for normal basis. We shall be trying to look into the normal basis inverter in GF2 power of 8, consider the scaling and squaring operations and optimizations which we are seeing in the polynomial basis, again work them out in the normal basis. We shall be trying to understand about the hierarchical decompositions in normal basis GF2 power of 8, GF2 power of 4 and finally GF2 power of 2, and finally obtain end-to-end mapping for getting the the functional equivalent output as that of an AES S-box, and we shall also be concluding with some finer points and comparisons with the polynomial basis representation. So, with this sort of idea, let us start. So, let us just a quick recap about the normal basis. So, in the normal basis representation, again you have an irreducible polynomial typically denoted as Px, which is defined over the Galois field GF2 power of m, and suppose alpha is the root of this polynomial Px, then the set which is like denoted as alpha, alpha square, alpha to the power of 2 power of 2 and so on till alpha to the power of 2 to the power of m minus 1 is called as a normal basis if the m elements are linearly independent. That means, for GFP power of k, we can easily understand that we can generalize it for GFP power of k, where it should be alpha to the power of p power of 0, alpha to the power of p power of 1, so on till alpha to the power of p power of k minus 1. Okay. So, you can easily understand the relation if you plug in p equal to 2 between this and this. And likewise, right, if you, so this is another, we will be considering composite fields like what we are doing in polynomial basis. So, we will encounter fields of this type, right, GF2 power of 4 square. That means, there are two parts in this argument, each of them has got are elements of GF2 power of 4. So, in this particular representation, the basis or the normal basis would be represented as alpha and alpha to the power of 16. Okay. So, essentially this would be my basis for GF2 power of 4 square. Likewise, for GF2 power of 2, my basis would be omega and omega power of 4. Okay. So, essentially and finally, when we go down to GF2, right, essentially to the lower basis, then we will find out that the basis will be denoted as say omega and omega square. Okay. So, we shall be seeing like in more details about how to use and manipulate these basis elements in our discussions. So, getting started, this is my field or the starting field, like I have taken an element in GF2 power of 8 and converted it into the composite field denoted as GF2 power of 4 square, and I have used the irreducible polynomial like in the last class. So, this polynomial is Ry, which is equal to y square plus tau y plus mu. Okay. So, therefore, tau and mu are my variables and this is my polynomial. That means, if I take any two elements in this field, which is say GF2 power of 4 whole square. So, that means, I can take any element and that element would be denoted as Ax plus b. Okay. So, that means, if I just quickly try to work out like an element here, like suppose I take GF2 power of 4 whole square, that means, this is my like a corresponding field element and I take an element for this field and denote it as say Ax plus b. So, that means, A and b both belongs to GF2 power of 4. Okay. So, likewise, I can take another element in the field and denote it as say Cx plus d. So, C and d are again elements from GF2 to the power of 4, and if I consider a product. So, this is again like I am considering or writing this element in the polynomial basis in the last class. So, then essentially if I multiply them, that means, if I multiply Ax plus b with Cx plus d, then I will get elements which are like AC x square plus so on, right. So, note that this is now no more in this field GF2 power of 4 square because I get a degree which is 2. Okay. So therefore, here comes the purpose of my irreducible polynomial. So my irreducible polynomial, as I said, was x square plus tau x plus mu. Okay. So therefore, what I will do is that in order to reduce this, I will substitute, instead of x square, I will substitute tau x plus mu. Okay. So you can easily understand now my degree is in x. So therefore, this gets back into the composite field. Okay. Of course, for normal basis, you have to do slightly a different type of manipulation, but the basic idea is the same. Okay. You have to rewrite the result back in your basis. Okay. So you have to write it back in your original basis. Okay. So with this background, I mean, we can again, like get back to this discussion. So let us get back. Let us now try to talk about the normal basis representation. So in the normal basis representation, interestingly, you still have the same equation, which is y square. When you are doing a reduction, you are writing, instead of y square, you are writing tau y plus mu. But interestingly, you see, as I said, probably if you remember, like that the basis in this case is y power of 16 and y. Okay. So therefore, the basis for GF2 power of 4 whole square representation is y power of 16 and y. So that means I will represent an element in this field now, unlike your polynomial representation, which was say ax plus b. Now we will write it as a y to the power of 16 plus by, because y to the power of 16 comma y is my basis. Okay. So therefore, I will write it as a y to the power of 16 plus by. That will be my representation in the composite field. So now you can note that means that y power of 16 and y both are elements of this irreducible, or both are roots of this irreducible polynomial. Okay. So now if both of them are roots of irreducible polynomial, that means from the theory of equations, you know that the sum of the roots, that is y power of 16 plus y, will be equal to tau. Okay, will be, so in this case plus and minus are same because it is in GF2 arithmetic. So therefore, we can write that, we can instead rewrite this as 1 is equal to tau inverse y power of 16 plus y. Okay. So that means y power of 16 plus y is equal to tau, or we can also write just squaring both sides, y power of 32 plus y square is equal to tau square. Okay. So these are some manipulations that we will be using in our future simplifications. The other important thing is the product, which is mu power y power of 16 into y. Okay. And that is equal to mu, because this is this term. Okay. So therefore, the product, that is the product of the roots y power of 16 and y, is equal to mu. Okay. So now let us consider like a multiplication in the normal basis. Okay. So this you can actually understand. I mean, if we just ignore the like the scribbling on the slide and just concentrate on the problem. Okay. So it's not very complicated. So for example, like let me consider two elements in the field GF2 power of 4 square. So note that one of the elements is gamma 1 y power of 16 plus gamma 0 y. Okay. So you note that how we have represented the element. Okay. Unlike your polynomial basis representation, because here y power of 16 and y are my basis. So I have to express it in that basis. Unlike in the polynomial basis, my basis was x comma 1. So therefore, I had expressed it using the indeterminate x and 1. Okay. So here I have to express it using y power of 16 and y, and therefore the two components are again gamma 1 and gamma 0, where gamma 1 belongs to GF2 power of 4 and gamma 0 also belongs to GF2 power of 4. Okay. So now, if you multiply this with another element, which is say delta 1 y power of 16 plus delta 0. So now you can easily understand, if I multiply, then I will get y power of 32, because y power of 16 and y power of 16 will get multiplied. So I will get y power of 32 here, and the other terms will be gamma y power of 16 into y, and that is gamma 1 delta 0 plus gamma 0 delta 1 y power of 16 into y, plus the term gamma 0 into gamma 0. So I have missed out a y here, so please add a y here. Okay. So there should be a y which is added here. Okay. So let me just try to do the correction here. Okay. So we should actually add a y here. Okay. So there should be a y here, and therefore, right, I get this term as y power of 16 into y, and this term as y square, because here this and this gets multiplied. Okay. So therefore, I get gamma 0 into delta 0 y square. So now we will have to again bring the result back into the original basis, because you note that I have got y power of 32, I have got y power of 16 into y and y square. Okay, none of these are basis elements. So therefore, right, what I do is I replace y power of 32 as y square plus tau square using the equation that we have just now seen, and y power of 16 into y we can write that as mu. Okay, so that is my mu, and likewise I have got gamma 0 into delta 0 into y square. Okay. This is still not in my basis. Okay. So therefore, what I do, because my basis is y power of 16 and y, so I have to bring the result back in y power of 16 and y. Okay. So it is slightly more involved than the polynomial basis, but it can be easily understood. What I do is that now I write this in two parts. One is where I have got the y square part. Okay. So the y square and then is multiplied with gamma 1 delta 1. Plus the other term is gamma 0 into delta 0. So this I write in one part, and the other part is the constant term. Okay. So now I do a trick. So the trick is I replace y, I replace 1 wherever there is a constant, and I replace 1 using my simplification which I have just now seen, and that is nothing but writing that as tau inverse multiplied by y to the power of 16 plus y. Okay. So therefore, right, what I do here is that I take these terms, okay, and I write y square as tau y plus mu, okay, but I do not write only tau y plus mu, but I write tau y plus mu into 1, and 1 is nothing but tau inverse multiplied by y power of 16 plus 1. Okay. So that is essentially this part of the equation. Okay. So then the other part is this part, that is gamma 1 delta 1 tau square plus mu and so on, and then again this I multiply this by 1. So I write that as tau inverse multiplied by y to the power of 16 plus y. So now you note that all the indeterminates that I have got are involving only y and y power of 16, and therefore that is my basis. Okay. So now if I just expand this, then I get terms which are involving y power of 16 and y, and therefore, right, I have rewritten my result back in my normal basis. Okay. I started with my basis y power of 16 and y, and I have got the product also expressed in the same basis. Okay. So therefore, these are my two parts. That means this is my the first part, and this is my lower part. Okay. And therefore, the corresponding results essentially stands for my two components of my result. You can actually make some more simplification. For example, the coefficient of y power of 16 is written here as like if I just multiply, for example, tau inverse with tau square, I will get tau. So that is gamma 1 delta 1 tau plus mu tau inverse with this part, which is gamma 1 delta 0 plus gamma 0 delta 1. This is this part. Okay. And then I add it with like this part, that is I just keep on doing the same thing, and I have got mu tau inverse. So I can take mu tau inverse common from here, and I have got this as gamma 1 delta 1 plus gamma 0 delta 0. Okay. So now you can actually easily see that this can be rewritten as gamma 1 plus gamma 0 into delta 1 plus delta 0. So this you can like this part you can simplify as here. Okay. And therefore you get the final result, which you can simply denote as gamma 1 delta 1 tau plus a theta. Okay. And this theta is nothing but this part, that is essentially this is your theta. Okay. So likewise, the coefficient of y can also be interestingly written as this part, and I am not going into the details, but I leave it to verify, for you to verify the details. You can write that as gamma 0 delta 0 tau plus theta. These are the two components of my corresponding result. Okay. So now like with this right, we can actually derive the inverse equation. Okay. So let us see how we can do that. So now once we want, so when I want to derive the normal basis inversion in GF2 power of 4 square, my basic technique will be same as that I did for polynomial basis. Okay. So now I will write this result as delta 1 y power of 16 plus delta 0. Note that I have again okay, so I again have actually done a mistake here, which is the basis, right, is y. So therefore the y should be here. Okay. This is something that we have to be always careful, okay, because the basis is something irregular compared to the polynomial basis. So therefore, right, the result is essentially like, so we basically, when I am trying to do when I am basically trying to or whether when this inverse relationship is satisfied, that means when I multiply this polynomial with this polynomial, I get 1. I get 1 as a result. Okay. and therefore, right, equating the above product which I just now derived for the multiplication of two inputs to 1. Okay, then 1 is nothing but tau inverse y to the power of 16 plus y. Okay, so therefore, I can actually match the coefficients of y power of 16 and I can match the coefficients of y separately. Okay, and therefore, right, what will happen is tau inverse, that is tau inverse, which is the coefficient of y power of 16, will be equal to gamma 1 delta 1 tau plus theta. Okay, and tau inverse will also be equal to gamma 0 delta 0 tau plus theta. These are two parts. Okay. So therefore, right now if I elaborate this and I do a little bit of simplification, then I can express the result delta 0 and delta 1 kind of in a similar way as as what we have done in the context of polynomial basis. Okay. So therefore, finally, right, you can simplify this, eliminate and essentially solve this simultaneous equation to get your result delta 0 and delta 1 in this form. Okay. So you can note here that there is an inversion which you are doing right now if you want to get the delta 0 and delta 1 outputs, but this inversion is now in GF 2 power of 4. Okay. So therefore, you have basically expressed a higher dimension inverse in terms of a smaller dimension inverse, and that is essentially the trick which we have also done for polynomial basis, and we are trying to adopt that for normal basis as well. Okay. So therefore, right, we basically now we can actually like do a similar thing for the GF 2 power of 4 inverse also. So the GF 2 power of 4 inverse, we will now express it as a GF 2 power of 2 whole power of 2 element, but the normal basis now will be z power of 4 comma z. Okay. So therefore, I will take elements say like gamma 1 z to the power of 4 plus gamma 0 z. So these gammas are capital to denote that they are in the they are essentially in the base field. Okay. And then I do a whole power of inverse, but my polynomial is now say z squared plus tz plus n. Okay. So again, you can observe that I can write my delta 0 and delta 1 in a similar fashion, but these inverses now are in GF 2 power of 2. Okay. So therefore, what I can do is now I can write this GF 2 power of 2 as GF 2 whole square. Okay. So therefore, I can decompose this further and my basis is now omega square comma omega or w square comma w, and therefore, the inverse of g1 w squared plus 0 whole, g0 whole inverse is essentially nothing but d1 w square plus d0, but the polynomial is done modulo of the irreducible polynomial w square plus w plus 1. Okay. So basically, right, what I am trying to do again is kind of similar to what we have done previously, is to express an element in GF 2 power of 4 whole square in terms of GF 2 power of 2 whole power of 2 whole power of 2. Okay. So that is essentially my final objective. Okay. So therefore, right, what I am trying to do is that if you see the representations, when I am trying to write an element in GF 2 power of 4 whole square, okay, then my element was in the form of gamma y power of 16 plus, or I can write here as a gamma 1 and gamma 0 y. Okay. Likewise, when I am writing it in GF 2 power of 2, that means when I am expressing GF 2 power of 4 as GF 2 power of 2 whole power of 2, then I am writing a gamma which is an element in this field as gamma 1 z to the power of 4 plus gamma 0 z. Okay. So these are essentially, this is my decomposition that I am doing, and likewise when I am writing these as GF 2 whole power of 2, then I am taking one of these capital gammas and I am writing this as d1 w squared plus d0 w. Okay. So therefore, these are my corresponding field elements and I have to do this operation with respect to the corresponding irreducible polynomials. Okay. So that is the whole idea. So therefore, right, you can observe that this is my inverse in GF 2 power of 2 whole power of 2, where these inverses or these smaller inverses are now in GF 2 power of 2. Okay. But if you rewrite again, if you do the same thing for the smaller field now, then again you will have inverses, but these inverses are in GF 2. Okay. And in GF 2, the inverse, any element's inverse is inverse, because the inverse of 0 is defined as 0 and the inverse of 1 is also defined as 1. Okay. So, therefore, you can actually ignore these inverses in the smaller field, and with some simplifications you can see that you will get D0 and D1 as shown here. Okay. So, you see that it is very simple in this field, because essentially you are just writing D0 as G1 and D1 as G0. So, basically the inverse in this field is actually kind of free. There is no computation that you need to do. Okay. So, and that is also, like you can also observe this, that this also means that the squaring in this field will also be equally easy. Okay. So, the squaring and the inversion both in the normal basis in the lowest field is actually free, as unlike your polynomial basis where you probably need some XOR gates. Okay. So, therefore, right, I mean, so that is an incentive for going into the normal basis. Okay. So, likewise, what we can do is now we can actually try to look for optimizations like what we have seen in the polynomial basis context. Okay. And you can note that the tau actually appears in both the equations, and therefore, exactly like in the polynomial basis we can set tau as 1. Okay. Note that I cannot set mu equal to 1 for the reasons which I told in the last class. Okay. Essentially, right, this essentially then would become a subfield of this particular field. Okay. So, therefore, right, I will set tau as 1, but I will not set mu as 1. Okay. But at least setting tau equal to 1 gives me a nice opportunity for optimization. For example, now this becomes in this form, and therefore, you can write this as gamma 1 gamma 0 plus this whole square you can actually write as gamma 1 plus gamma 0 whole square. Okay. Because like again when you are taking a square, then 2 is 0. So, therefore, this is equivalent. Why do you do that? You save some gates, because otherwise you have to do 2 squarings and then 1 addition, but now you have to just do 1 addition and 1 squaring. Okay. And also you can write this in a nice, or you can draw this in a nice way. For example, here is my corresponding diagram for doing the normal GF2 to the power of 8 inverter, or you can say actually this is a normal GF2 to power of 4 whole square inverter, because my element has been written in GF2 to power of 4 square. So, therefore, now when I have got 2 components like gamma 1 and gamma 0, you can see, and you can exactly do a 1-to-1 match between this equation. So, you see that what I have got is gamma 1 into gamma 0. So, this goes to my smaller inversion, which is my GF2 power of 4 inversion, which is denoted here, and the inputs to this is nothing but gamma 1 into gamma 0. Gamma 1 into gamma 0 is done by this multiplier, and then I add it with gamma 1 plus gamma 0 whole square into mu. Okay. So, this operation, okay, so this operation is actually what we have seen previously, and is called as the squaring and scaling operation. Okay. So, this operation where you are doing a squaring and you are multiplying with a constant is called as a squaring and scaling operation. Okay. And that is done by this block, where you basically square and you scale, that is you multiply with a constant. Okay. So, once you have done this and you are doing this the input is the XOR of gamma 1 and gamma 0, and that is what you are squaring and scaling. Okay. So, therefore, once you have this part and you have got gamma 1 into gamma 0, you basically XOR them to get your result, which you feed to this GF2 power of 4 inversion, and therefore, right, you now get this part as your output, and in one case you multiply with gamma 1. For example, for delta 0 you multiply it with gamma 1. So, I take gamma 1 and I multiply here and I get delta 0, and likewise here I get gamma 0 and I multiply here to get delta 1. Okay. So, therefore, right, this is quite easily understood from this diagram. And finally, right, once you have done this, right, you can actually observe that internally you are basically doing GF2 power of 4 inversions and GF2 power of 4 multipliers. So, now you need to know the circuit for doing a GF2 power of 4 multiplier. Okay. So, therefore, right, let us take a look at the GF2 power of 4 multiplier. Remember, my elements in GF2 power of 4 have been now, or can be isomorphically expressed in GF2 power of 2 whole power of 2, and therefore, the elements here are gamma and delta. Okay. So, gamma, as I told you, is that nothing but gamma 1 z to the power of 4 plus gamma 0 z, because my basis is z to the power of 4 and z, and likewise delta is equal to delta 1 z power of 4 plus delta 0. Okay. So, if I now multiply them, okay, of course, maybe you should note few more things, that is the basis is z power of 4 comma z, which are the roots of this irreducible polynomial z square plus z plus n. Okay. And now what is this n? So therefore, right, what I have is that z power of z. So that means like z square is equal to z plus n, and exactly like what we have done for gf2 power of 4 square, we can do it for gf2 power of 2 whole power of 2 also. Okay. So what is that? We can write now that z square plus z is n when I want to do my simplifications, and I can also write z to the power of 4 plus z is equal to 1. Okay, because that is the sum of the two roots. And therefore, write z to the power of 4 equal to z plus 1, and that is z power of 8 is equal to z square plus 1. Okay, I have just done squarings on both sides. Also, the product of the two roots, that is z and z power of 4, should be equal to this constant n. Okay. So therefore, now I am ready to do this multiplication. So if I do this multiplication, again I will have got terms like z power of 8, because z power of 4 and z power of 4 will get multiplied. I will have terms like z power of 4 into z, for which this will be my corresponding coefficient. And likewise, I will have delta 0 into gamma 0 z square. Okay. So now what I can do is I can replace the z power of 8 as z square plus 1. So basically, I just take this simplification, that is z power of 8 is equal to z square plus 1, and I plug it over here. The product of this is written as n, okay, and I get this part. So likewise, again I have to bring the result back into z power of 4 and z, which is my basis, and therefore, right, I just do again a similar trick, which is I replace like z square as z plus n, and I get two parts, that is one which has got essentially z, and the other part which is a constant. But now I replace this one, okay, by because I have to write 1 as z power of 4 plus z. Okay, so therefore, if I do that, then I just plug it over here, and finally, right, so therefore I plug in this z power of 4 plus z. Okay, and if I do that, that means I basically, instead of 1, I write this z power of 4 plus z. Okay, and the other term already has z, which is fine, which is in my basis. Z is a basis element, and therefore, right, I split my result into two parts, one which has got z and the other which has got z power of 4. Okay. So this product will again have now more multiplications in the subfield gf2 power of 2. Okay. So therefore, right, this is so what we have seen till now is that we have seen how we can essentially get the result in gf2 power of 2 power of 2. Okay. So basically we started with gf2 power of 4 whole square. We did our multiplications in gf2 power of 4. We saw how we can do multiplications in gf2 power of 4 by expressing them as elements in gf2 power of 2 whole power of 2. Okay. So now we are in a position to derive the like the corresponding equations of the underlying fields. We basically have to consider one very important step, which I already tried to point out in the circuit diagram, which is the squaring and the scaling operation. Okay. And that is the crux operation, the crux of the operations, why the normal basis representation is so efficient, okay, or so compact, and that we will study in the next class. Okay. Thank you.